Hey everyone, and welcome back to All About AI Tech. Today's topic is gonna blow your mind. Transfer learning. Imagine this. You've trained a super smart AI to identify cats in pictures. Millions of data points, countless hours, tons of compute power. A real beast of a model. But then, bam. You decide you need to tackle a completely different problem. Maybe classifying X-rays or identifying molecular structures. Do you start from scratch? Absolutely not. That's where transfer learning, TL, comes in. It's like taking that cat identifying AI and teaching it a new trick, like instantly giving it the ability to recognize completely different types of patterns. We're not talking about just slight tweaks either. We're talking about leveraging that pre-trained model, that colossal wealth of knowledge already encoded, jumping across domains and crushing the performance benchmarks for tasks its creators never even imagined. You're effectively saving years of development time while massively enhancing the performance compared to starting from nothing. Let's take a look at some really cool examples in computer vision. Remember, in computer vision, CV will give the AI an image, and it produces some meaning from it. Now, think about the sheer scale of images required to train a great image recognition system. We're talking millions of images that have been carefully labeled by experts. That amount of data isn't always available or affordable, especially in areas like pathology, astronomy, material science, and more. That's where TL saves the day. Instead of starting a new task from scratch, building an image classifier from the ground up, we can now take an already well-trained and robust vision model, even one pre-trained on the ImageNet dataset, 1.2 million images, and fine-tune it to the classification task at hand. We're saving significant time and resources and achieving accuracy far greater compared to trying to build a model for the task from nothing. For instance, imagine wanting to classify galaxy morphology. That's mind-bogglingly difficult, takes years of expertise, and would require a very large dataset to construct a model from scratch. But using a large pre-trained model already well-versed in classifying all sorts of images, this problem actually turns out to be simple and achievable quickly. This is a true testament to TL's potential in computer vision. Transfer learning isn't just limited to images, It's changing the entire field of natural language processing, NLP. Think about the sheer volume of text data around today. Every book, blog post, website you can think of, plus all the information that's locked up in corporate databases. Training LLMs, large language models, from scratch is akin to building a behemoth with colossal financial and ethical implications. Training on something as broad as the internet requires you to wrestle with the problem of garbage in, garbage out, and ensure that all of the information your model is fed on is both reasonable and ethically curated. This challenge is compounded by the costs involved in designing massive datasets of words, grammar, facts, and opinions for model training. Fortunately, we can use the same idea with language models, too. We create a pre-trained model, a basic language model initially trained on enormous quantities of text, which captures the underlying knowledge structure of language, and then we transfer this pre-trained model to specific tasks like classification or question answering. We then fine-tune the model using smaller datasets designed specifically for these new tasks, rather than creating them from scratch. This approach dramatically reduces training times, resource needs, and cost while retaining strong performance levels. For example, imagine a business requiring a model to classify customer survey text based on sentiment, positive, negative, or neutral. Using transfer learning on an off-the-shelf large language model already proficient at predicting the next word in a sentence allows a company to create an accurate sentiment analyzer rapidly and efficiently. Let's shift gears and talk about drug discovery. This field is a fantastic example of where transfer learning is making huge waves. Think about it. The molecular structures of different molecules can be depicted as graphs. We can use graph neural networks, GNNs, to learn the relationships between molecular structures and their properties. Getting large labeled datasets is time and resource intensive in this field, which makes it particularly challenging. For example, generating large amounts of experimental data to create a good training set and identify new drug candidates can cost millions, or even hundreds of millions of dollars. We can dramatically decrease the cost of drug development efforts by using transfer learning on pre-trained GNNs. Then we can use the pre-trained models and fine-tune them on smaller, focused datasets to identify promising candidates. These pre-trained models already have an understanding of the underlying structure of molecules, so you only need to use limited amounts of task-specific data to improve accuracy and develop a high-performing model for a particular task. The models also acquire the ability to transfer and, for example, knowledge learned from the pre-training of a GNN model to predict the toxicity of a certain type of molecule could be readily transferred to predict the bioactivity of a different type of molecule. This can drastically improve the efficiency of drug development by saving years of time, drastically lowering research costs, and enabling the development of new drugs to fight diseases at a low cost. Now, let's talk about a particularly cool technique called knowledge distillation, KD. It's closely related to transfer learning, but with a twist. Think of it as a mentorship program for AI models. You've got a large, powerful, highly capable model like GPT or Llama 2 that knows a tremendous amount. That's your teacher. But using such a behemoth can be sluggish, expensive, and memory-intensive. Instead, you train a smaller, more efficient student which will perform similarly for certain tasks. The teacher model produces very detailed predictions at a high resolution that are used to train the smaller student model that will be used in production. It then uses a loss function to compute how well the student model mimics the teacher's responses to refine these weights. The student model, despite having a fraction of the teacher model's parameters, benefits from the vast knowledge already baked into the teacher. This distillation process allows you to create models that are lean, clean, and efficient, yet still deliver high levels of accuracy. It's ideal for tasks requiring low latency, such as classifying medical images in real time or powering chatbots used in customer services. The process also offers major benefits for improving performance and efficiency, but unlike transfer learning, only the outputs are copied and reused from the teacher to student. The teacher model doesn't necessarily need to be available in this process after training. Here's another exciting domain that's transforming how we do AI, specifically in fields where data is scarce. Few-shot learning, FSL. Imagine you only have a handful of labeled examples, and you need to train your model to distinguish between different tasks. Getting a robust model in such cases is challenging because the model might memorize instead of learning. This makes the model prone to overfitting and poor generalization. Few-shot learning aims to mimic the surprising ability of humans able to quickly understand things based on a handful of examples. This involves providing the model with a small set of labeled examples as a reference and a separate larger set of examples without labels, thus allowing the model to learn some generalizable patterns. With the advent of large language models, LLMs, that are typically pre-trained on enormous datasets, it is possible to build this type of model. You provide the model with a small set of labeled examples as a support set. It will then treat this support set as examples and classify data based on its similarity to examples in the support set. Few-shot learning is transforming fields like medical diagnostics and material science, helping us build accurate models even when extensive datasets are unavailable. It significantly minimizes resources needed for data accumulation and cuts training time and costs down while maintaining excellent accuracy levels for given tasks. Here's another advanced meta-learning approach, MAML, that shows incredible potential. MAML learns the best starting points for training. It does this by adapting the model's initial parameters based on related tasks. Imagine you're building a model for medical image analysis. MAML allows you to first train on sets of diverse, related images before fine-tuning for the particular condition you want to identify. The ability to adapt the parameters from other tasks helps to train models much faster and more accurately even in low data regimes. This approach contrasts with traditional methods that begin training from scratch, which often requires substantial time and computational resources. MAML has demonstrated exceptional results in various applications like robotic control, few-shot image classification, and natural language processing by facilitating the rapid adaptation of trained models to new, unforeseen situations with small sets of data samples. This makes MAML is useful for scenarios where rapidly deploying models without significant delay is a major advantage. Domain adaptation tackles the challenge of adapting models trained on one type of data, source domain, to effectively work on another type, target domain. This is crucial in cases where there's a significant difference in the characteristics of both datasets, possibly arising from differences in populations, hardware, or acquisition settings. The aim of domain adaptation is to this can be addressed by using domain generalization that involves incorporating diversity into the training process, making the model more robust to variations. Alternatively, various domain adaptation techniques can be used that actively attempts to reduce/align the two distributions. For example, adversarial training, where a network is trained to classify data based on which domain it comes from, source or target, while at the same time, the feature extractor model tries to fool this classifier, creating models that generalize better to the target domain. Domain adaptation is increasingly important for tasks like medical image classification where data from different hospitals, countries, or populations vary substantially in their characteristics. It supports better utilization of the model across different domains, eliminating data scarcity issues. Self-supervised learning, SSL, is another impressive technique for building models. It's particularly useful when labeled data is scarce because SSL trains models without using any labels whatsoever. The model learns internal representations of the data by introducing an auxiliary or pretext task, such as masking parts of a sequence, and then having the model use neighboring data in order to reconstruct the missing information. By learning how to recover details based on unlabeled data, we can create models that show unexpected abilities for classification and other downstream tasks, such as those seen in BNDR, Costas et al., 2021. That is, a pre-trained SSL model successfully transferred across multiple tasks and subjects, even though its training had never included any labels. Self-supervised learning has many advantages, notably mitigating label dependency and enhancing feature generalization when training models. This approach is becoming particularly useful in areas such as medical imaging and genomic analysis where labeled data is difficult and expensive to obtain. This powerful technique is poised to play a pivotal role in the future of AI by enabling models to learn from abundant, unlabeled data while performing effectively on smaller labeled datasets. Federated learning, FL, addresses major privacy concerns associated with the use of data by organizations. In FL, the training process is decentralized across multiple entities without sharing data. The process is as follows. A model is sent to distributed nodes, typically those of separate organizations that possess private data. The nodes then train models locally, sending updated models to a central server. This server then aggregates model updates or weights into a globally updated model. This is then resent to the nodes for further optimization, repeating the process until the overall model has converged. Federated learning enhances data security and protects user privacy. This approach proves crucial for applications such as those in the banking and healthcare sectors. The model can also be trained with minimal training over. For example, if researchers at various universities want to collaborate on developing an emotion recognition model using EEG data, they can each train their models on their own data in a secure and private manner. The resulting models are then aggregated into a global model by leveraging federated learning, fostering collaboration while maintaining data privacy. Research has also shown that this approach can surprisingly improve the overall accuracy and robustness of models. Transfer learning isn't just some cool theoretical concept. It's being used everywhere right now. We've already touched on a few examples in computer vision, NLP, drug discovery, but there are many more. Think about self-driving cars. Transfer learning helps these vehicles adapt rapidly to new environments and driving scenarios using their experiences in others. Or consider robotics. Transfer learning makes it possible for robots to learn new tasks in a faster way by leveraging the information from other, similar tasks, even in vastly different domains. In manufacturing, it enhances fault detection and quality control. It's even affecting how we do finance, from fraud detection to personalized banking assistance. It has far-reaching impacts on fields such as healthcare, education, and agriculture with unexpected improvements in speed, accuracy, and cost across a wide range of disciplines. The applications are practically limitless, and it's a rapidly expanding field with exciting innovation occurring daily. While transfer learning is utterly transformative, there are, naturally, still challenges to overcome. One key challenge is the need for high-quality, diverse datasets. If your source dataset isn't well suited for the target data, you may actually lose performance. Selecting the right source, both the pre-trained model as well as the data it was trained on, is a key decision that needs consideration. Another challenge lies in the assessment of which elements of a model transfer well from one domain to another. Some models perform remarkably well, while others may not provide the same performance gains. This further indicates the need to improve these methods and create more reliable and generalizable models. The complexity of calculating performance and assessing the transferability of models requires further investigation and the development of new metrics for comparing the performance of different models across various tasks and domains. The integration and combination of various techniques such as those mentioned above, including domain adaptation, few-shot learning, and self-supervised learning, with pre-trained architectures holds immense potential for enhancing transfer learning capabilities across fields. Future work should continuously seek to address these challenges and explore new approaches to further unlock the transformative abilities of transfer learning. The future of AI lies in harnessing the vast potential of these methods and improving how we build models in data-constrained environments.